All right, we're looking today at the energy required to assemble charges. To assemble charges. Okay. I'm going to do a few different configurations and we'll try to build up a framework of how we can know how to do this every time. We're starting with the premise that there are charges available, but they're all an infinite distance away. So they're all an infinite distance from each other, and therefore the potential energy, more specifically the electric potential energy, stored between any two of those charges is going to be effectively zero, since they are an effectively infinite distance away from each other. So the initial energy of the system, the way we've designed it, is zero. Next, if I take a charge out from infinity and I bring it into here, call this Q1, it is still an infinite distance away from all other charges, because all the other charges are literally an infinite distance away. So the electric potential energy did not change. Therefore, the change in electric potential energy for the first charge is equal to zero. Here's another way of looking at that. I only see one charge in the region. There is no second charge in the region. So it would be K times Q1 times 0 divided by R gives me 0. So just one more way of saying the first charge is free. On to Q2. Q2, I'm going to have it come in from this way, boom, and put it right there. Note that I'm just doing point charges and spheres, so I can use this version of the energy stored electrically. If it was a different shape, then I'd have to use different equations, which we'll discuss more as we get into electric fields. These two charges are a distance r1, 2 away from each other. Now we have some energy stored in our system. The change in electric potential energy for the second charge is equal to K Q1. Back that up a little bit. Potential energy final minus potential energy initial. The initial was 0. Just wanted to get that explicit. Equals, now we could just focus on the final. K Q1 Q2 over R1 2. That's the energy to bring the second one in. A note about this value. This could be a positive or a negative value. If we are dealing with two positive charges, then we've got positive and positive multiplied to be positive. If we're dealing with two negative charges, negative and negative multiplied to be positive. And if we're dealing with a positive and a negative, positive multiplied by negative, no matter the order of operations there, will give you a negative change in potential energy. So there's a loss in energy when or there's a loss in potential energy, more specifically, when two opposite charges are brought close to each other. And there's an increase in potential energy when like charges are brought close to each other. Let's move on to the third charge. For our third charge, I'm going to have it come in from down left. Q3. Q3 is some distance away from Q1. That's R13. It is some distance away from Q2. That'll be R23. The change in electric potential energy for Q3, I'm going to do on the right. How much energy does it take to bring in the third charge? Well, the 1 and 2 did not change at all. The only change we have is this any interactions involving Q3 and the other charges. So there's change in electric potential energy 1,3, and there's a change in electric potential energy 2,3. Like we had earlier, the initial energy was 0, so I can just focus on the final. So it'll be K Q1 Q3 divided by R13 plus K Q2 Q3 over R23. Okay. Important things of note. There's always only 2 charges in that numerator. Each semester I see someone put 3 charges in there. It's like, no. It's all interactions are one-on-one interactions, not one-on-one-on-one. Okay. Next, we are not including the Q1, Q2 because that's something that happened in the past. If I want to know the total amount of energy, then I will add everything together. But for now, I'm just thinking how much energy to bring this Q3 into the mix. Now this could be positive, this could be negative. It all depends on what's positive and negative here, what's positive, negative here, which distance is bigger. And we have a lot more parameters here that will make it difficult to say outright, oh, this is an increase, this is a decrease. You have to go through these things one at a time. So just like I did here, looking at every single term, except twice as much, because there are 2 terms to consider. Third is done. Next, let's bring in a 4th charge. I'm going to put a 4th charge right here. And the reason Q4 is going there is because I don't want any overlaps in my R's when I draw them. Because there's going to be an R14. There's going to be an R24. And there's going to be an R34. That means that there's going to be 3 terms for the electric potential energy to just bring the 4th charge in. This will include an interaction between 1 and 4, an interaction between 2 and 4, and an interaction between 3 and 4. And I'm just doing this as a shorthand for what I set up here. Okay, those are each individual electric potential energies. Again, because the initial was 0 because everything's an infinite distance away at the start, I can just focus on the final potential energies. K, Q1, Q4 over R14. K, Q2, Q4 over R24 plus K, Q3, Q4 over R34. And that'll be my change in electric potential energy for the fourth charge. What we've found so far is the energy to bring in individual charges. Now, let's put it all together. Let's find the energy to assemble all of these charges. To assemble all of these charges, that will be change in electric potential energy total will be the change in electric potential energy for the first charge plus the change in electric potential energy for the second charge plus the change in electric potential energy for the third charge plus the change in electric potential energy for the fourth charge. One at a time. Looking at our blue equation up top, first charge is free. Boom. Second, Q2. Let's copy this down for Q2. So that'll be change in electric potential energy 2 will be K Q1 Q2 over R12. Next, energy to bring in the third charge in. That's going to be this stuff over here. Plus K Q1 Q3 over R13 plus K Q2 Q3 over R23. And lastly, for the fourth charge, K Q1 Q4 over R14. I'm going to run out of space. Plus K Q2 Q4 over R24. I barely have enough space left for the last one. K Q3 Q4 over R34. That is our change in electric potential energy total. All right. As a warning, there could be a different way of thinking about this. Sometimes a question instead asks, what is the work done to assemble a charge, instead of what is the change in electric potential energy? In that case, realize that the work that needs to go in or out of some system will be equal to the change in electric potential energy total if your kinetic energy does not change. All right. So we need to do one more assumption for this problem. We need to assume that the kinetic energy initial equals the kinetic energy final. If that's the case, that would be, for example, they're stationary way at that infinite location, and they're stationary in their spots where we put them here. Maybe we glued them in place, maybe we clamped them down with wood or something. But somehow the kinetic energy at the very beginning and the very end stay the same. In which case we can omit that term and say that the change in electric potential energy total is equal to the work done to assemble charges. And there we go. Two different ways it's commonly asked: work or change in electric potential energy. Had we had a fifth charge that was brought in, there's a pattern that I'm hoping that you can see. Had there been a fifth charge, that's a nice orange charge, then there would be a K, Q1, Q5 over R15 plus K, Q2, Q5 over R25 plus K, Q3, Q5 over R35, and lastly, K, Q4, Q5 divided by R45. Okay. As you can see, the more charges you bring in, the much longer this electric potential energy equation gets. There's a table in the book showing how this progression gets larger and larger. You're basically adding on whatever value you're on. So this is the fifth charge. It adds on 4 more terms. A sixth charge would add on 5 more terms. A seventh charge would add on 6 more terms, etc. And there's a table showing how these numbers get pretty big pretty fast in the book. All right. Hope this helps you.